The next talk is first of two invited talks, and it's a pleasure to have Rose Yu here. She's an assistant professor at UC San Diego at the Department of Computer Science and Engineering and the Data Science Institute. So her research lies at the interplay between physics and deep learning and physics-informed machine learning methods. And specifically, she is developing a lot of interesting tools for learning with large-scale spatial temporal data, which is actually perfect for the competition here, and is also perfect for the competition that IARAI did 2 days ago on weather predictions. So that is actually also one of her topics. She uses these new tools to research in climate and weather modeling, but also for turbulent flow prediction and many other exciting topics. And one very recent cool paper that I saw, which was in Europe's, I think last week, was the use of ideas from physics in deep learning for the automated discovery of symmetries. So this is also a really interesting topic. And today, Professor Yu will explain to us how graph neural networks can be used for learning spatial temporal dynamical systems. Okay, Rose, please.
Oh, thank you. Hi, thank you, Maria, for the kind introduction. And can you hear me okay?
Yes.
Can you see my slides?
Yes.
Great. It is a great pleasure to come and give a talk here at this workshop. And it's actually a very interesting project that I have been discussing with Mario for a while. So today I'm going to talk about some tools that might be useful for this particular challenge of science of science. And I would like to see hopefully more work on graph neural nets applied to different interesting problems. So my name is Rose Yu, and I'm assistant professor at the University of California, San Diego in the computer science department. So I direct the spatial temporal machine learning lab, and here is the logo of our lab. As you can see that there is a rose in the middle of the logo. And then there's also a hidden letters, SNT stands for spatial temporal. So that's the theme of our lab. Our mission is to advance machine learning to understand and drive insights from large-scale spatial temporal data. So that's why we have spatial temporal learning in the title. But just to give you some ideas of what I mean by spatial temporal learning, here is a video showing the traffic patterns in LA, where I studied for many years. So this traffic flow changes from morning to night, and the bubbles represent the accidents happening at different locations. So traditionally in transportation research, many models rely on very strong assumptions about driver behavior. So oftentimes these models cannot capture realistic traffic patterns. Now with advancement in sensing technology, especially with several thousand sensors, detectors on the roads, on the roadside cameras, we have high frequency real-time data collecting information about traffic. So the question is, can we leverage this type of data to design more realistic traffic models for congestion control? The second example is a sport that I love, and I used to play basketball when I growing up. So in basketball, we have real-time tracking cameras tracking behaviors of basketball players. So for the first time ever, then we have a large amount of data collected over space and time. So in a 90 minutes basketball game, we can collect about 2,000 events over 1.5 million data points. So the question is, can we leverage this type of data to study human behavior in competitive sports and help coaches design winning strategies? So these two examples hopefully give you some idea of what I mean by spatial temporal learning or learning spatial temporal dynamics. So in transportation, sports, and many other fields in science and engineering, The data that's being generated in this field contain very rich space and time information. So if we can actually learn the spatial temporal dynamics, then we will be able to make progress towards real-time decision making in science and engineering problems. So spatial temporal data is quite different from traditional machine learning applications such as images or text data, because spatial temporal data has intricate patterns. As an example, let's consider the application of traffic forecasting. So this figure shows the sensor reading of 3 road sensors. And as you can see here, we're visualizing the speed in terms of mile per hour. So, and then over number of hours. So this is basically recording in real time from 3 road sensors. As we can see here, all the 3 road sensors are very close to each other. However, their patterns are very different because the yellow sensor is on the opposite side of this highway, and therefore it has very different patterns. And road 1 and road 2 are on the same side of the highway, so they have very similar behavior. So as you can see here, traffic data in this case contains very intricate temporal dynamics. So we need to build models that can capture this type of temporal dynamics. On top of that, the sensors are correlated to each other due to spatial proximity. So in addition to modeling spatial temporal dynamics, we also wanted to capture the spatial correlations in the time series. So the challenge of modeling this type of data is non-stationarity, meaning that the behavior or statistics of the data is changing over time. So this makes it very difficult for traditional time series models, such as ARIMA models or ARMA models, which are type of linear models, to capture this type of non-stationary behavior. Instead, we use deep learning, which is a type of nonlinear models. So deep neural network has seen a lot of success in other applications, and sort of in this area of spatial temporal learning, we're among the early people who adopted deep learning for time series modeling. So we use recurrent neural nets for capturing temporal dynamics. As we can see here, we have an encoder and decoder architecture, where the encoder takes a sequence of historical patterns. So x0 to xt represent the speed of multiple sensors over past t timestamps. And then the decoder will take the hidden states generated by the encoder and then initialize the hidden states from the decoder and then generate predictions xt plus 1 to xt plus t. And these represent the future forecasts of the time series. So mathematically, given the input state xt, hidden state ht, and output yt, an RNN is essentially a nonlinear hidden Markov model. Essentially, it maps the hidden states from previous timestamp ht minus 1 into the future hidden state ht, and then the output, which in our case is the prediction of the next timestamp, is again a nonlinear function map from the hidden states at time t. So this is a classic method for modeling nonlinear dynamics, and RNNs was invented to model in time series probably 30 years ago. But what's special about traffic pattern is the spatial dependency, because the sensors are correlated to each other, and then even though the sensors are close to each other, their spatial patterns can vary. So how can we model spatial dependency in this case? Well, when we look at images, it actually can be thought as in pixels distributed on a regular grid. So we can model that with convolutional neural networks, which exploit location, locality, and translation symmetry in the data of images. However, when we move from images to this type of sensor networks, we can no longer model the spatial dependency with a regular grid, but instead we need a irregular grid representation to model the traffic flow. So our idea is to think of traffic flow as diffusion processes on an irregular grid, and then we derived a new type of convolutional operator that can operate on this kind of directed graphs. So in this graph, the nodes represent different sensors, and the edges represent their spatial proximity. In this case, the spatial proximity is calculated based on travel time. So what is diffusion convolution? And that is our key contribution in this paper at Clear. So the idea is that we wanted to represent the grid, the irregular grid, as an adjacency matrix, which is a network. Right? So this adjacency matrix has each element defined as some distance measure, some inverse distance measure between two nodes. So Vi and Vj are two nodes, and then here they represent two sensors. Distance net represents the network distance, and that is calibrated using travel time. So this metric essentially quantifies the proximity of spatial adjacency between the two nodes. Given the adjacency matrix, we can define the in-degree and out-degree matrix, which is the column sum and the row sum of this adjacency matrix. So our diffusion convolution was inspired by the fact that there is very nice graph theoretical results by Tianxiang et al. In 2017, which quantifies the stationary distribution of a diffusion process on a graph. Essentially, it's saying that we need to calculate this matrix known as a random walk matrix in graph theory. So a random walk matrix is the inverse of the out-degree matrix multiplied by the adjacency matrix and raise it to power of k. So the stationary distribution of the diffusion process, which is a vector over the discrete number of nodes, can be represented as an infinite summation of weighted adjacency, a random walk matrix. So theta is a parameter that represents the diffusion speed over different nodes. And then this random walk matrix raised to different power of k represent diffusion over k number of steps. So in the kind of classic models, the parameter theta need to be identified beforehand or manually constructed. Our idea here of diffusion convolution is to let the neural network learn this kind of parameters in the diffusion process, and that's lead to the diffusion convolution. So essentially, given the input at time t, xt, so xt represents the features at time t. So in traffic forecasting, the features can include the velocity, the speed, or the volume of all the sensors together at time t. So we need to calculate this type of transformation of the input features xt using the random walk matrix. However, the parameters here, theta O, which represent the out-degree diffusion, and dO, which represent the in-degree diffusion, are trainable weights in neural network. And we can learn these through backpropagation. And then xt is the input at time t. So this convolution essentially transforms the feature using the graph information. So this can be thought as a special type of graph neural networks, but for dynamical data. To realize what it's doing in terms of diffusion convolution, we can think of traffic density as concentrated density in the center of the node. So a diffusion convolution will essentially propagate the density into different adjacency neighbors. So a zero-step diffusion will concentrate the density in the middle, and then a one-step diffusion up to k-step diffusion will propagate the density into the neighboring nodes. So how can we combine diffusion convolution with RNNs? Well, in this case, remember we are using a recurrent neural network to model the temporal dynamics. So as the RNN will transform the input xt into the hidden states through a matrix multiplication. So in this case, it assumes that all the features in xt are independent from each other. So there is no spatial dependency in the RNN architecture. In order to model the spatial dependency, we can simply replace the matrix multiplication with graph convolution. So using graph convolution, we can transform the hidden states using the graph, the diffusion convolution operator that I just introduced. So in this case, we can model spatial dependency and temporal dynamics simultaneously. So this type of transformation can be generalized to many other sequence models. So here I'm only showing an example of a recurrent neural network, but in principle, you can use it for a gated recurrent neural unit and long short-term memory units, or any other type of deep sequence models by simply replacing the matrix multiplication with graph convolution. We show that this type of operation reduced to graph convolution when the graph is static and undirected. So to put this together, right, we wanted to design a deep learning model that can forecast the time series of traffic. So we are representing the traffic data as a sequence of graphs because the nodes represent the sensors and the edges represent the spatial proximity. And then the features on the nodes are evolving over time and represent the speed change over time. So our output is also a sequence of future graphs represent the future speeds over time. And we wanted to design a type of diffusion convolution or RNN, or in this case, we use gated recurrent unit or GRU, which is a memory-based recurrent neural net in a sequence-to-sequence framework. So specifically, given the input graph signals over time, we use an encoder and decoder architecture. The encoder will take in the sequence of historical graphs, and then using our designed diffusion convolutional operator, it can transform the input signals into some hidden states. After that, we can copy the hidden states from the encoder to the decoder. And again, using our diffusion convolutional recurrent layer, we can decode the future graphs from the hidden states using the decoder. So that's kind of the overall architecture of this model. I wanted to say that this model was proposed a couple years ago, and at the time it was a state of the art. So it was actually deployed at Google for forecasting traffic patterns in Google Maps. And then there have been a lot of follow-ups after this paper. People have proposed various type of improvements and over this key idea of diffusion convolution RNNs. And here I'm presenting the results that we presented at the time, and we evaluated this model on 2 real-world data sets. One is in LA, the other one is in the Bay Area. So the size of the graph is 207 nodes, and then for Bay Area, it has 300 nodes. In total, you have several million observations in terms of time points. So we looked at the forecasting mean absolute errors in mile per hour. So the average speed in the US is about 70 to 75 mile per hour for highway traffic. So we looked at the comparison of our model, which is DCRNN, with different type of baselines. So historical average is a simple method that was used to forecast road network traffic. ARIMA, VAR, and SVR models are shallow models for time series forecasting. Fully connected layer or LSTMs are deep learning models for forecasting time series. And for LSTMs, it does not have the explicit component to model spatial dependency. And when we look at the forecasting error over different forecasting horizon for 15 minutes up to 1 hour, we can see that our model achieves the best performance across all different horizons. For 1 hour ahead forecasting, the error is about 3.5 mile per hour out of 70. So at the time, I think the best methods can only forecast accurately for 5 minutes ahead. And with this type of deep learning models, we were able to push the forecasting horizon for up to 1 hour. We also see similar patterns for the Bay Area traffic forecasting problems. And in this case, the forecasting performance is even better, and we achieved a 2.2 mile per hour error out of 70 miles on average. Because we're using a diffusion process to model the traffic patterns, we could also look at the learned weights from the convolutional kernel and understand what is actually the diffusion center of these processes. So we'll take out the weights from the diffusion convolution and then map it to the sensor network. So the neural network has learned to identify the diffusion hubs of the traffic in LA. So specifically, it has identified this area. If you're familiar with LA, then you will know that this area, the center of is the center of Hollywood, and there are a lot of exciting sightseeing and viewpoints in this area. And the center is actually the downtown LA area. I think this part was a puzzling part where we couldn't figure out why this was identified the diffusion hubs. And later we had to look at the map and try to figure out where does it lead to. And it turned out this actually road will lead to the Disneyland in LA. So it shows some interesting patterns that were automatically identified by this type of model. Just to understand like why this model can do better than LSTM-based models, we visualize the predictions from our model versus baseline. So this shows a mile per hour in terms of speed over different number of hours. So the blue line is the ground truth, and the orange line is a prediction from our model. The green line is a prediction from the baseline. So as we can see here, the orange line can fit the dip quite well compared with the baseline. It kind of verified the hypothesis that because the sensors are correlated to each other, by modeling the spatial dependency explicitly, we can better anticipate the changes in the traffic patterns. In this case, this kind of change can caused by either the accidents or rush hour traffic. So by modeling spatial dependency, our technique can better anticipate these changes and then fit the time series better than the baseline models. So as you can see here, we're using a graph neural network to model time series. But the limitation of this work is that we assume that we know the graph structure. So the graph structure or the adjacency matrix was explicitly constructed beforehand to represent the spatial proximity. In some other cases, we might not even know the underlying graph structure to model the dynamics. So how can we infer the graph dynamics while modeling the time series in a forecasting setting? And that's the second paper that we explored in terms of relational inference. So as a simple example, this figure was coming from a reference paper that we used in our work called dynamic relational inference. So in this case, we're looking at particle dynamics. So there are in total 5 particles, and they travel through space and time. So these particles are connected by a hidden spring, and we actually assume we don't know the underlying connections between the springs. So the spring obviously will change the dynamics of these particles, and the goal is to forecast the future trajectories of these particles, but at the same time, we want to infer the underlying graph in this interaction dynamics. So that is different from the previous work I talked about, where here we wanted to do 2 tasks at the same time, where we want to model the dynamics of the particles, which is a forecasting setting. At the same time, we wanted to infer the underlying edges. So that basically led to this line of work called neural relational inference. The previous work, that example I showed you here, was only focused on the static relational inference, which means that when the particles are connected, starting from the beginning, they will be connected for the rest of the dynamics. So the edges are not changing over time. And in this paper, we studied a much more challenging case, which is the dynamic relational inference. So let's consider the 2 particle scenario, right, where the 2 particles starting from this location, and the orange particles start from here, the blue particle starts from here. So when these 2 particles travel in the space and time, and then there is a hidden link that starts to connect with these to connect these 2 particles. Obviously, when the 2 particles are connected, their trajectories start to bend because of these spring forces. And after they travel for a while, we will take out the spring. So that's corresponding to second state change in this red-yellow line. And once the spring was taken out, then the particles start to travel freely in a straight line again. So the goal here, right, in this very simple synthetic example, is to infer when does this change happen, or when this type of edges are formed or removed by looking at only the trajectories of the particles. And that's basically the neural relational inference problem. So given spatial temporal trajectories, we wanted to infer the hidden graphs in this dynamics. And it has broad range of applications. For example, we can look at the social dynamics. For this particular workshop, we can use relational inference to infer the connections between scientific topics, the concepts, while making forecasts into the future. We can use that for particle physics to understand the hidden physics, or we can infer the communications in traffic patterns. So the previous work in neurorelational inference is only limited to the static relations, and here we're looking at a much more challenging setup. We can formulate this problem as a probabilistic graphical model. So in this case, we have trajectories over time, and then X1, the subscript, represents the timestamp, the superscript represents the particle index or the agent index. So you can see that the gray circles are observed data. So this particle number 1 will travel through time, so that's x1 to xt, and then the second particle in the middle has a superscript 2, and that's the second particle. So these also travel through time when we observe their trajectories. So what we don't observe is this latent variable, which is represented as a hollow circle, z12. So 1, 2 represents the interactions or edges between particle 1 and particle 2 at time 1. And because the dynamics is the relations are changing over time, so this hidden variable z is also time dependent. So therefore we have a subscript t represent the changes in the relation. So this is the graphical model representation of this problem. Specifically, we have n particle trajectories from I1 to IN, and n is the total number of particles. For each particle I, we have a trajectory x1 to xt, and we also have the hidden relationship of zt for particle I and particle j. So zij is essentially an edge in the graph, and this graph is also changing over time. So we wanted to learn so this type of data can be represent the jointer probability over the conditional distribution of the trajectories multiplied by this hidden representation, the hidden distribution P of z given xt and xt. So we can split the joint distribution according to this format, and then we proposed a deep neural network based framework combined with variational autoencoders to infer this type of hidden variables z. So let's lead to our dynamic multi-agent relational inference model. And this is a latent deep generative model based on variational autoencoders. So essentially, we take the trajectories of multiple agents or multiple particles, and then we will basically construct the interactions using a type of encoder. So this will take pairs of observations from the agents and construct this kind of pairwise trajectories over time. And this is our interaction encoding. After that, we put that into an encoder, which corresponding to this type of architecture. So this type of encoder is a spatial temporal dense net. So this is a sequence over time, and we use actually a temporal convolutional network to map this interaction encoding into a couple of hidden states. And then we use different resolutions to model the interaction at different temporal scale. So we have 2 different resolutions here to map the input data into hidden representations. We also include pooling layers and residual layers to capture this intricate dynamics. And after that, we will use a fully connected layer to generate the predictions of interactions, zt. So this zt is actually a vector over time. So it represents each pairs of interaction over time. So that's the inferred zt, which then is sampled from the hidden states of the encoder. And each zt is a distribution over, it's a binary variable, represents the probability of which there is a link happening between agent I and agent j. And using this type of inferred interactions, so we can then decode the trajectory into the future. So this is actually a construction task. Given the condition on the latent states, z1 to zt, we can generate the predictions, which is again the trajectory over time. So the high-level idea behind this model is that we want to infer the hidden relations at different timestamps given the trajectories. And then we use a temporal CNN, essentially in this case, a temporal CNN with residual blocks to decode, to encode the trajectories. And then we use message passing graph neural networks here to decode the trajectories from the hidden states. So I'm not going to go into details of how VAEs work, but essentially it's a degenerative model that optimizes a lower bound of the likelihood because of the probability distribution of this problem. And then this lower bound is known as evidence lower bound or elbow. So this is a training objective function in this model. Just to show you like what this model can do, we compared our method with different type of, this is on the synthetic data. So in this case, we're looking at particles with periodically adding and removing the interactions. So we call this inference period, which is basically the inference period is how many times we're generating this latent interaction z of t hat, which is the inferred interactions. And the dynamic period represents the ground truth interactions, which is the frequency of which we add and remove the links between the particles. So because we really don't know because we're only given the trajectories, we don't know how often these links were added or removed from the trajectories. So we actually don't know the ground truth dynamic period. And then we're looking at basically how the inference period, but we can control the inference period, which is how often we generate this latent variable. And of course, when the latent period and the dynamic period match each other, right, then we can see the inference accuracy is very, very good. For like, as the inference period becomes more and more frequent, then the accuracy drops. So that is unexpected because as we have more edges over time, the prediction problem becomes much more challenging. But then when we have, for example, 40 timestamp, there's 2 edges, then the prediction accuracy for the edges is about 92%. So we can accurately infer the edges. But then when the inference period is smaller than the dynamic period, right, which is on this top angle, we can see lower accuracy, but it still learns sometimes. It's on the lower triangle. So we can see that it has lower accuracy than the correct dynamic and inference period, but it can still learn to some extent, right? Which means, if we make inference faster than the ground truth dynamics, then we can still learn to some extent. But if we make inference, higher, less frequent than the underlying dynamics, then we can't really learn well in terms of underlying interactions. So compare with our model with the baseline model, which is a neural relational inference baselines, our accuracy is much higher than the baseline neural relational inference. So here we're looking at 5 particle cases of length 50, and then our input is timestamp 10 timestamps, and our output is 40 timestamps. So the relation will change periodically every 40, 20, 5 timestamps. So again, we can see that because of this dynamic relational inference mechanism, our model significantly outperforms NRI in much more dynamic scenarios, especially when we flip the edges in a much more higher frequency. Well, then we apply this model to infer interesting patterns in basketball play. So here we are viewing, the trajectories of 2 real-world basketball NBA plays. So the red line is a particular team, and then the blue line is another team. So that corresponds to different teams. So this is on a half court over time. So we apply our model to infer the hidden links, which is represented as dashed lines, during the play. So we can sort of see that the top row represents the same team coordination. So this blue line, right, is connected with the same color. So you can see how the long-range connection is being inferred from looking at the trajectories only. And then the bottom row corresponds to the competition patterns. So they're connected by opposite players of same row, but from different teams. And then again, we can see that there, especially when this player is closer to the basket, how the attention of different players are started concentrate on this middle player as an offense mechanism during a game. So we can see, especially on the here, when this player has the ball and it's on the 3-point line, right? There's a lot of links connected to this 3-point point players, and then we can see that basically people wanted to gauge the potential of catching and defend this player in the 3-point line. So okay, so to conclude, right? I give you two examples to show that GNNs are efficient tools for modeling spatial temporal dynamics. I introduced the DCRNN, a diffusion convolution RNNs, to model the node dynamics, assuming a fixed graph. So we applied this to traffic forecasting problem and achieved state-of-the-art performance in traffic forecasting. And I described the diary dynamic relational, multi-agent relational inference, which is the type of GNNs that I can learn the edge dynamics and making forecasts at the same time. We apply that to model the dynamics of basketball, and then we can infer interesting patterns during play of coordination and competition. So there are a lot of open problems, obviously, for GNNs, and I think this community is well posed to tackle these type of challenges, right? For instance, the data in Science4cast forecasting is much larger in terms of number of nodes over time. So there's a scalability issues that need to be resolved for modeling GNNs for large graphs over time. Sometimes, the spatial temporal events is not happening at the regular frequency. Like for instance, the changes of the accidents or, the combination of the concepts merging together, they can happen at different spatial and time scale. So designing GNNs to model irregular spatial temporal events is also another challenge. And obviously, we wanted to do long-term forecasting, and hopefully for science-to-science problems, we wanted to be able to forecast the future trend in the next 100 years, right? Because science does not evolve as fast as basketball or traffic. So if we can do long-term forecast, then we will have a much better view of what's going to happen, in terms of the science and engineering problems. So with that, I wanted to acknowledge some of the funding agencies of this work. And if you have questions about our work, you can email me at this address or follow me on Twitter. Thank you.
Thank you very much. That was really interesting. So many different applications. It's really cool.
Thanks.
Yeah, there are a lot of questions in the chat. Let me start with the first question by Michael Kopp. Hi, Rose, great talk. Looking at your diffusion process for the incomplete road network, so not all roads that exist modeled, and it brings a small subsample of the real road graph. Do I understand it correctly that the GNN learns sync or source node behavior?
So let's see. So it's not right. So because we are looking at a sub road network, right? And it's actually impossible to model the complete network. So the GNNs learn the diffusion process. So it mimics the behavior sync versus source, but then because we're modeling an incomplete graph, so the density is not conserved. So there is no supposed assumption in our model to capture that kind of sync and source behavior. But the diffusion, the diffusion dynamic itself, it basically mimic how the traffic density is propagating from one node to the other. And that's a good question.
Okay, thanks. So I should mention it's really interesting topics that you're working on, because the Institute has actually a competition on traffic forecasting and
yes,
a competition on
aware.
weather forecasting. So it's basically the perfect overlap. So yeah.
Exactly. Yeah, we are very excited to see that challenge. We actually we are part of the challenge, I think, a couple of years ago for traffic forecasting. I think the challenge there is really there's a large scale number of the traffic density comes in the form of videos, where in this case we're modeling on lower dimensional dynamics. But I think the data that was provided by IARAI is extremely interesting, and right now my students are actively looking at that.
Oh, I'm sure they're happy to hear this. Okay, so the next question by Christian Eichenberger, who also worked on the traffic forecast competition. Um, Many thanks for the interesting talk. You use MAE in evaluation. How did you deal with the time steps without any data? Yeah.
Oh, so in our case, we first perform imputation beforehand, right? For traffic, the sensors are connected at 12 hertz. So we basically average the data, and then in the sense that computing the aggregated time speed over time and transforming that into a regular time series. And then for this timestamps without data, we call it missing data. We will perform mean filling and backward and forward mean filling to fill in the missing data first. And then for the MAE, we calculated for the time step that only have data. So that's like for non-zeros. Yeah, for non-zeros, we compute MAE.
Okay. Okay. Now there's a next question by Pedro, who was actually one of the organizers of the weather forecast competition this year, where there was a workshop 2 days ago. I was wondering how you could encode external feature that affect the whole graph, like weather. And I think this is very related to a question that comes later by Marvin McCutcheon. He asked whether there are additional information or how you could capture potential additional information like spatial realities, semantic information, or geometry that you can kind of not encode into graphs.
Right, that's a great question. So like we have another paper which kind of separate, time evolving features versus static features. But the high level idea is that we have a graph neural network that maps the sequence of graphs into some vector representation, right, hidden representation. And then for weather patterns, we can use a different type of architecture to map this kind of input data into hidden representations. So now we have two sets of hidden representations. What people usually do is that they will concatenate the hidden representations together. So in our model, even though we haven't done that before, but I would imagine we can have a DCRNN model that generates hidden features for temporal graphs, and then we have another type of neural network that generate hidden features from the weather patterns or external features, depending on whether or not it is time dependent or it's a graph, right? Or it's a static feature. And then we will concatenate the hidden features together to form augmented hidden states, and then the rest is the same.
Mhm. Okay, I see. I see. Interesting. Um, so there was a follow-up question by Christian Eichenberger. You showed a plot comparing speed predictions with ground truth. Where on the timeline does the prediction start in the plot, and how long is the time window for the input? Or is it a slicing window of what size? Is the
Right.
situation shown in a recurrent rush hour or spontaneous jam?
Yeah, that's a very good question. So like here, the plot we showed is the 1 hour ahead forecasting. So in our case, we have 12 timestamps. Right. The data is not 12 parts. It's actually 12. So every 5 minutes, after aggregation. So we have 12 points for 1 hour, and then that's basically the forecasting window. We did use a moving window approach to extract the training and testing sequences. And the plot I showed is basically the concatenation of all the 1 hour ahead forecasts rolled out for 24 hours. So start, 12 points ahead, and then you start, kind of generate 12 points, and then we will use that as restart again and generate another 12 points and put them together into a 24-hour trajectory.
Okay, thanks. Then there's another question, a question by Yin Chu. Thanks for the great talk. I'm wondering if the dynamic model is capable of some level of generalization to transfer learning. For example, if you train it on one team, will it be able to adapt to another team with few or even no training data? Probably that's on the base basket.
I see. That's a fantastic question. So yeah, so in our case, we're not looking at the transfer learning case. Our model is an unsupervised learning model. So you learn the distribution of the trajectories, and then make inference about the edges for a relational inference setup. So in principle, all right, because it's unsupervised model, we can, just train it. After the model is trained, we can use it to make inference on a different type of team. So in principle, I would say yes, it could generalize well, right? But it's not a transfer learning, meaning like, we're not doing any type of domain adaptation or inference adjustment, inference time adjustment for different team. But I think that would be like an interesting future direction.
Okay. So we are already out of time, but I use my position as a chair anyway to ask you one last question. So if you think about the Science4cast competition, one difference probably to the data that you have is that we have an exponentially growing graph, which is probably then kind of different to predict, I would guess. But I would be very curious on your thought on this. Whether you
So when you say exponential graph, is that the dynamics or the edge dynamic or the node dynamic?
The number of edges grow exponentially.
I see. Yeah, I mean, I think it's a very challenging problem. And in general, let's say, because the edge grows all over exponentially, so perhaps like one idea is instead of modeling the absolute numbers in the growth, right, we can have some sort of hybrid model to actually model the rates of the growth. So then, the neural network would, instead of learning like how many new edges being added, we can just model the dynamic of, there's some underlying equation that we sort of know, and then we use GNN to infer the parameters of this equation. So that might be a more feasible path.
Okay. Yeah, I very much hope that we can continue working on this and try this actually out.
Of course.
Okay, cool. Thanks so much for this very interesting talk, which fits perfectly to the research topic here of the of IARAI and of Science4cast. So that was really
Thank you
really
so
good.
much.
Thank you.
Yeah, okay. Thanks for organizing this wonderful workshop.